able to get a copy of that. And if there's any extras, just kind of pass them up to the front so I can pass them out later if necessary. So you can see the outline is on the back side of the syllabus. And let's just start with the outline. My name, office, email, phone, office hours, et cetera, are all here. Please note that I have an office hour for the hour before your class every Monday, Wednesday, and Friday. And then also another office hour on Monday at 1:30. So there should be plenty of time for you to come see me if necessary. If anybody does need to see me and it's just not convenient to see me during the office hour that week or whatever, then I'll certainly be willing to set up an appointment. But just give me a couple of days' notice if you can so that I could do that. The textbook for the class is the 8th edition of Schenkel and Bowles. You do not need to buy the physical book unless you want to. Most of you took ME 301 where you automatically were provided, well, I guess you had to pay for it through your fees, but you were automatically given an electronic copy of this book. So your access to McGraw-Hill is supposed to be for like 2 or 3 years, something like that. So you should be able to just access the textbook the same way you've done previously. But if you took ME 301, let's say more than a year and a half ago, before it was required to buy the electronic version and you just have a hard copy of the book, that's fine. Just make sure you have the 8th edition. Not that thermodynamics has changed much in 100 years, but certainly the example problems are different. The order of the materials is different from edition to edition. So please make sure you have the 8th edition. If for some reason you already own a previous edition, in fact, even the 7th edition, I don't think there's any differences in the section numbers. Some of the materials covered slightly differently. That would probably be okay, but still make sure that you get the 8th edition so you can do the proper homework problems. The homework problems in the back of each section are definitely different from one edition to the next. Nonetheless, that's the 8th edition, the one with the inside of a gas turbine on the front of it. Don't forget to get the book, please. As far as the grading goes, 10% for homework, 25% each for the 2 midterm exams, the dates of which are shown on the back on the syllabus, and then 40% for the final exam. I will note that I grade on what I like to call a modified class curve. Roughly it's going to be 90% A, 80% B, 70% C, et cetera, et cetera. But still, it's not always going to be exactly like that. Sometimes my exams are a little bit too long or a little too short. Sometimes they're a little too difficult or a little bit too easy. So the grades are going to kind of vary a little bit from the standard curve. But more or less, it's going to be a curve. And I'll let you know following each exam what the grade would be based on the scores you've gotten. So it should be pretty clear how you're doing in the class. I'll also note here that well, I state that exams will be part closed book, part open book. I don't know exactly how things are going to be this particular quarter. Certainly in ME 301, I would often have a closed book section, but in 302, we're not learning any basics anymore. We're just using the basics we've already learned to kind of learn more advanced topics in thermodynamics. So I may not actually have a closed book section. And then when it says open book, I don't know if it's going to be open book, open notes, open book, closed notes. I don't know if I'll let you use a note card or not a note card, but I'll let you know at least a week before any exam what the format's going to be. Nonetheless, the 2 midterms, the dates are on the syllabus, and the final exam is on Wednesday of finals week at 9:10 in the morning. I only have this one section of thermodynamics, so I don't have the ability to give a second final exam or a make-up final exam. So everybody needs to take the proper final exam, again at 9:10 on June 6th, which is a Wednesday. So please make sure that that date is available to you. You know, don't plan on going away early for your summer break or anything like that if you have final exams. I think that's just good advice. Anyway, moving on, prerequisites. You all have to have at least a C- or better in ME 301. Everybody needs to show me proof of having met that prerequisite. You can just show me on your portable device, you know, just log into Bronco Direct and pull up anything that has your grade of C- or better on ME 301. Show it to me after class, before class, in my office, anywhere you can find me. Or you could just print out the page that has that information on it. If you do print it out, make sure it has your name on it. And I don't mean write your name at the top. Make sure it's an official page with your official name up there so that it's clear you're actually showing me your own grades. But everybody has to show me that proof, and it has to be done before April 16th, which is the last day that I can drop you. If I don't get that before the 16th, then I'll drop you anyway. Or if, well, at least I have the option of dropping you. The other option as the university allows me to give you a failing grade regardless of how well you do in ME 302, which I don't want to do. So please make sure you have the prerequisite and don't forget to show me. You've got 3 full weeks to do so, so there's no rush. As far as homework, homework will be assigned daily. Actually, this is for the entire week. In fact, usually I do that now. I used to assign it every day, but I know pretty much what we're going to cover every day. So I'll give you the homework assignment at the beginning of every week, and then it'll always be due the following Wednesday. So these problems will be due next Wednesday, next week's problems the following Wednesday. And I'm primarily interested in your ability to set up the problems properly, use the right methods, make sure everything is organized and well illustrated. Quite frankly, it's very common to do a problem and have a wrong answer. There's so many ways to make wrong answers in this class: sign errors, math errors, conversion factor errors, et cetera, table lookup errors. So I'm not that concerned that you have the right answers. I'm more concerned that you have a good understanding of the methodology. That's primarily what I'm looking at. I also should warn you well in advance that there's only so many of what I consider to be really good problems in this 8th edition of the book. And the problems that I'm using, I've used before. This textbook was, like 4 years old now or something. So I'm sure that if you wanted to, you could find solutions out there in cyberspace to everything I've done. I don't want you to look at those. I mean, you can if you really feel that you have to, but I mean, the best way to learn the material is to learn it on your own. Make sure you understand how to set up the problems. If all you're doing is copying somebody else's work and turning it in as your own on the homework, and then you have to take an exam, I mean, how are you going to know how to set up anything? How are you going to know where to look up the data? How are you going to really know what some of the pitfalls are for the different types of problems unless you do the problems yourself on the homework? So please resist if you can. I will post the solutions of the homework problems on Wednesday after class, but I'm going to do it the old-fashioned way. I find that I'm now, I don't want to call myself a relic, but I'm the senior member of the ME faculty now. And I kind of do things the old way. I don't really like to use all the online resources that are available. I'm not going to actually assign anything from the McGraw-Hill website or anything like that. But nonetheless, I will post the solutions in a glass case right outside my office every Wednesday after class. And that's where you're going to be able to see the solutions. Now again, I'm sure students have taken digital photos of my solutions in past years, and you may be able to find them elsewhere. But again, please resist looking at those, at least until after you've done the problems yourself, okay? By the way, if I find that all the homework solutions that are coming in, or a big majority of them, are just exact copies of either what's in the solution manual, which by the way, you're not allowed to see or own, and could actually be kicked out of school if you're found with one. But if you begin to turn in as a whole, solutions that are clearly not your own, I may just decide to not even bother with homework anymore. But I don't want that. I'd really like you to do homework. I'm going to grade them myself. I'd like to give you that kind of feedback. And, so please don't take advantage. Anyway, last but not least, the drop policy. I'm sure you're all aware that engineering students are not allowed to drop after a particular deadline date, which is April 16th this year. After that, if you decide not to take the class, then you have to withdraw from the university, and that's between you and the dean's office. You have to show serious personal and compelling reasons. You will not be allowed to just simply withdraw from one class or another. You'll have to completely drop out of school, and after April 16th, you lose your fees, and no refunds at that point. So please make sure that you really want to take this class. Now, if you don't want to take the class, then, just don't take it. Take it, well, you don't have a lot of choices, I guess. You can take one of the CAP classes that we'll offer either in the summer or next fall. But I would suspect that most of you are going to stick it out in this class. Nonetheless, just be aware, after April 16th, you have to have a death in the family, serious personal injury, something like that, in order to drop the class. Let me also note at this point that the last day to add is the 5th day of instruction, which I guess will be next Monday. But the last day to drop is 2 weeks after that. I can't add students after the 5th day of instruction, so if you are going to drop, please drop as soon as possible. That way the waiting list will automatically put somebody else into your spot. If you decide not to take the class now, but wait a week or two to drop, then I can't fill your spot. So please just be aware of that. So are there any questions on anything? Let me also just note that I'm not a stickler like some with regards to whether you eat in class or not. I mean, you generally don't want to eat in class just because it makes noise. And I don't care about the noise because I'm far away from you, but the person next to you might not appreciate hearing you crunching your Doritos and making noise with your plastic bags and all of that kind of stuff. So it would be best if you did eat in class, but if you're quiet about it, I'm not going to say anything. If you spill, then just make sure you clean it up. Also, I do understand that you all have lives outside of Cal Poly. If you're waiting for an important phone call, just make sure you put your phone on vibrate and sit over here by the door. And if that important call comes in and you need to leave, then just step out and take it. If you're coming into class late, again, just try to be as quiet as you can and find your seat as quietly as you can, just so that we don't disturb the class. And now we're recording this entire lecture, so also we don't want to disturb the cameraman in the back. So again, any questions on any of this? Right. And then the syllabus is on the reverse, so let's just take a very quick look at that. You can see that the first couple of days are review. In fact, I am going to review material for the rest of today's lecture. I'm not going to just let you go once I'm done with this little introduction. If you feel that you understand the material well, maybe you just took thermo last quarter, you could leave if you want to, but I'll just let that be up to you. Following that, I've identified which sections of which chapters that we're going to cover on each particular day. I've identified the topic. And you should know pretty well what we're going to cover any particular day. I should be sticking with the syllabus pretty accurately. So one thing I would always recommend is perhaps spend 15 or 20 minutes before class just reviewing the material in the textbook before you actually get to class and hear my take on the same material. At least if you do that, you'll kind of understand what we're going to be talking about. You'll understand some of the terminology. You'll perhaps have seen some of the notation and heard some of the discussion, or at least read the discussion of that material. I think it'll just make it a little bit easier for everybody to do well, in this particular class.
I was wondering, will these be uploaded this quarter or later?
I don't know. In ME 301, they were always able to give me the videos within like 2 days, and then I put them on Blackboard. Now, I don't have Blackboard set up yet because there's just nothing to put there. But when I start getting these videos, if indeed I do get them, then yeah, I'll put them on Blackboard as soon as I get them. So hopefully they will be available for you. Let me also remind everybody that the ME department has an online site. We just call it ME Online. It's part of Cal Poly's website, and there's all sorts of example problems there. There's sample lectures for certain material. I would definitely recommend that you look at that and see what material is available to you, and perhaps check out some of the sample lectures, check out some of the example problems that have been done. I think that'll help many of you to learn the material. Please keep in mind, I don't need to say this because you've all taken 301, this is certainly one of those courses that they warned you about in high school, right, where you'll probably have to spend 3 or 4 hours outside of class or every hour inside of class. If you don't have a good 12 to 15 hours a week, you're not going to do as good as you can or do as well as you can in thermodynamics. You're just not. You need to do the reading, you need to do the homework problems, you need to perhaps discuss things with study partners and really get a good understanding of the material. So if you're thinking that you can just kind of squeak by and do the minimal amount of work, it's very unlikely that that's going to happen. Now, certainly that's your choice, but again, I would recommend that you have that time available. If you don't have the time available, then you're just not going to do as well as you can. Certainly everybody wants to get A's. I would hate to have to give C's and D's to students who have the ability to get A's and B's just because they don't have the time to do well in the class. So just consider that a kind of a warning or a caution at the beginning of the class. Okay, so let me just continue with the introduction, and you can kind of follow along with the syllabus. I just want to identify the main areas that we're going to cover in this class. So first of all, the first general area will be cycles. Okay? Now in ME 301, you were supposed to have covered the break-in cycle, which is just the first of many gas power cycles that are covered. I guess it's chapter 9 of your textbook. So that's where we're going to start. We're going to start in chapter 9, after the review. But we're not just going to cover the gas power cycles. We're going to cover other cycles as well. Within the category of the gas power cycles, certainly we'll talk about the Brayton cycle, and that will be the emphasis, or at least one of the emphasis of chapter 9. But the Brayton cycle you learned about in ME 301 is just the simple Brayton cycle. We're going to cover various variations of the Brayton cycle, which you'd see in the real world, which will improve the performance, the efficiency, the power output of a typical gas turbine engine, which is really what the Brayton cycle is all about, right? A jet engine, gas turbine engine, Sometimes they're called combustion turbine engines. It's all the same thing. These are analyzed using the model we call the Brayton cycle. Nonetheless, we'll cover the Brayton cycle in some detail. We'll also cover a couple of the cycles that are used to analyze the performance of an internal combustion engine. We'll look at the Otto cycle, which is a pretty decent model of the gasoline engine, and we'll look at the diesel engine, which is a pretty good, maybe fair to pretty good model of the diesel engine, but at least it'll give us the ability to analyze these types of cycles. We'll then look very, very briefly at the Stirling and Ericsson engines, or cycles, I should say. You know, I'm not really a big favorite of these. There are really almost none of them out there in commercial service, so I don't really see any point in talking about those Ericsson and Stirling cycles, at least not in a lot of detail. Anyway, after the gas power cycles, we'll move on to the Rankine cycle. The Rankine cycle is a steam power plant cycle. So steam power plants are modeled using the Rankine cycle. We'll look at the simple Rankine cycle, and then we'll look at various variations to the Rankine cycle, as again one would see out in the real world. And then I may even talk a little bit about combined cycles. That's becoming very popular. Certainly combined cycles have been around for a long time, but you could run a gas turbine engine, and instead of letting the exhaust just shoot up the smokestack, run it into a boiler, turn water into steam, and use that steam to run a steam turbine. So you're basically not having to buy any more power or any more heat, any more fuel, if you will, but you're able to get a lot more work output because of the combined gas and steam cycles. So hopefully we'll have a little bit of time to talk about that. And then lastly, we'll talk about refrigeration cycles. We've all covered at least the basics in ME 301 of the refrigeration cycle, right? I mean, you covered heat engine cycles. By the way, the Brayton cycle, the Otto cycle, the diesel cycle, the Rankine cycles, those are all heat engines, right? You're putting some heat in and you're getting some work out. But we're also going to be covering the refrigeration cycles, but certainly in a lot more detail than what was covered in your ME 301 class. So that will be the last, and we'll cover the vapor compression refrigeration cycle, which is really the most common one. That's what you're going to see in all your refrigerators, freezers, air conditioners, ice makers. And we'll also briefly talk about absorption refrigeration cycles, which are used, but only on the large scale for commercial service. Actually, the analysis of an absorption cycle is really beyond this course, so beyond just a little bit of discussion, we'll move on from that. The second main category, besides cycles then, is thermodynamic property relations. So here is where we're going to start talking about the theoretical relationships that are basically the foundation of all of thermodynamics. We'll start with some general relations. We'll talk about some equations like called the Maxwell equations and Clapeyron equations. We'll look at some of the property relations. In other words, we'll see how different thermodynamic properties relate to each other. This is going to be more theoretical. I'm definitely not going to emphasize this. You know, if we were at Caltech or UCLA, very likely half of your second course in thermodynamics is going to deal with thermodynamic property relations, very theoretical stuff. In this class, I think I'll spend about a week just so we have a good basic understanding of the theory behind thermodynamics. But beyond that, we'll move on to more practical topics. Next, third area is mixtures, specifically gas mixtures. We'll look in general at the equations associated with gas mixtures. Then we'll specifically look at air-water vapor mixtures. If you look at the atmosphere all around us, the atmosphere all around us is an air-water vapor mixture, right? It's not just air, air meaning oxygen and nitrogen, but it's also water vapor. Sometimes there's a lot of water vapor, sometimes there's very little, but nonetheless, we really need to understand the nature of air-water vapor mixtures. Associated with this is a topic called psychrometrics, which is basically the property data associated with air-water vapor mixtures. And then we'll also talk about air conditioning. I mean, the whole reason you have air conditioning is to adjust the temperature and adjust the humidity. Maybe you need to make the air warmer and moister, maybe you need to make it cooler and drier, maybe you need to have a combination of both. So these are the types of processes that we're going to deal with when we talk about air conditioning. We're not really going to talk about the cycles at that point. We're just going to talk about the individual devices and try to figure out, you know, how does one analyze a process from the standpoint of the air that's being heated, cooled, humidified, or dehumidified. And then last but not least, the fourth area will be chemical reactions. And again, this is not going to be the emphasis in this class. We'll probably just spend a couple of days dealing with combustion, which is the only chemical reaction that we're really going to deal with in this particular class. So, these are the topics that are identified on the syllabus. And are there any questions on any of that? Good. So, with that then, I believe it's time for our review. So, again, if somebody just feels like they don't need the review, again, now's a good time to go. But nonetheless, I'm just going to spend the rest of the day going through some review. Okay. Now, again, I want to note, my handwriting can be awfully sloppy at times. I always blame my 5th grade teacher. I have a twin brother. He was in the other 5th grade class. His handwriting was just like mine until 5th grade, and then his became perfect, and mine just got worse. So, I'm doing the best I can. If you can't read something I've written on the board, just let me know, especially because this is being recorded, and I would like to make sure everything's accurate. Also, keep in mind that I do sometimes write the wrong thing. I'll say one thing and write something else. If you see that I've written something incorrectly, please correct me on that, just to make sure everything is accurate. So with regards to review, first, let's just keep in mind that there are all sorts of properties that we have to deal with here in thermodynamics. Properties are basically just observable or identifiable characteristics of a particular substance. Some of these properties are measurable and some are not measurable properties, and that's kind of the problem with thermodynamics. We don't have such thing as an entropy meter or an enthalpy meter or an internal energy meter. We only have things like pressure and temperature gauges, scales so we can measure mass, devices to measure volume. So when we talk about properties, sometimes we need to use the measurable properties so that we can find the value of the not measurable properties. And that's why we have all these thermodynamic property tables, right? You need enthalpy, you need internal energy, you need entropy. You can't measure them, so you use pressure, temperature, specific volume data to get those other properties, right? So the properties that are of interest to us typically will be pressure, temperature, volume. There's also going to be specific volume. Please note that I'm trying to show a difference between the capital letter V, which would be the total volume, units of cubic meters, versus the specific volume, which is cubic meters per kilogram, right? Note that the specific volume is just the inverse of the density, but we're rarely going to use density. The density is certainly an important parameter, but in thermodynamics, we always use the inverse of density, right? We use specific volume. So I'm rarely going to even discuss density, but I will always talk about specific volume. We also have internal energy and enthalpy and entropy. And then, of course, we have the specific properties, right? We would have specific internal energy, specific enthalpy, specific entropy. I'm going to try again real hard to make sure that all the variables right on the board are clear. There's definitely a difference between the total internal energy and the specific internal energy, the total enthalpy and the specific enthalpy. Just keep in mind that these specific properties are really just per unit mass, right? So if we wanted the specific internal energy, it's just the total internal energy over the mass. If we wanted the specific enthalpy, it's just the total enthalpy over the mass. And I'll just put etc. This would also apply to entropy. So these are just the main properties that we're going to deal with. And then let's also note that if we know any two independent intensive properties, then that sets the thermodynamic state, right? If we know any two independent intensive properties, then we can go into our tables, or we can use graphical means, or we can use equations of state, and we can find any of the other thermodynamic properties we want. So if we know any two independent intensive properties, then we know the state. In other words, we know all properties. Or maybe I should say that we know the state, therefore all other intensive properties. Okay? And again, this is why we have things like tables and equations, right? Now, please note that intensive means that it doesn't depend on the quantity. Okay, hopefully this is something that we remember from our thermal class. So for instance, if I have a cup of water at a particular pressure and temperature, and then I take a little spoon of that water out, it's still going to have the same pressure and temperature. If I take a little drop, it's going to have the same temperature and pressure. Clearly, temperature and pressure are intensive properties, right? Same thing with specific volume, right? The specific volume doesn't change whether I have a whole cup of that material or just a spoonful of that material or a drop of the material. But on the other hand, properties like the total internal energy, total volume, total enthalpy, total entropy, those are not intensive. Those would be called extensive properties, and those certainly do depend upon the quantity, right? If we have a cup of water versus a spoonful of water, clearly there's a much different volume, right? And the energy associated with that is going to be different, as will be the enthalpy and entropy, et cetera, et cetera. So again, this is something that hopefully was made very clear to you right at the very beginning of your thermal class, well, 301 thermal class. Another thing we should be aware of are phases, right? We know that substances exhibit different phases, right? So we could have a liquid, we could have vapor, we could have a solid. Sometimes we use the word fluid instead of liquid, but technically a fluid could be a liquid or a gas, so I'm not going to use fluid. Vapor, we could also call a gas if we wanted to. A solid, well, it's just a solid. But these are the three phases that we're going to have to deal with as we deal with various processes. Let's keep in mind that it's really the liquid and the vapor phase that are of most interest to us. When we deal with any of these cycles that I've mentioned, not the gas power cycle because it's always a gas, but the refrigeration cycles, the Rankine cycles, those are going to be cycles that at some point in the cycle will be liquids, and at some point in the cycle will be vapors, and at some point in the cycle will actually be a combination of both liquid and vapor. We call that a two-phase mixture, right? So let's just make sure we are aware of the different phases, and certainly the emphasis for many cycles is going to be the liquids and the vapors and the mixtures of the two. Okay, so another thing I want to talk about is temperature. So temperature T. Let's keep in mind that we generally use an absolute scale. In other words, Kelvin, which we just call K, or Rankine, R. I mean, you could put the little circle up top, for the degree sign, but generally you don't. If you see K, that's just a temperature in Kelvin, and R is just a temperature in Rankine. Keep in mind that if you are using temperature, let's say to look up data in tables, then it's typically in Celsius or Fahrenheit. But on the other hand, if you're using temperature in an equation, like let's say in your ideal gas equation of state or other equations, then if temperature is used within an equation, then it always has to be with one of the absolute temperature scales. And let's just keep in mind that temperature in Kelvin is just going to equal the temperature in degrees Celsius plus 273.15. And also the temperature in Rankine is going to equal the temperature in degrees Fahrenheit. And then plus 459.67. You can certainly round this down to 273 or round this up to 460 if you want to. But these are the official conversions that we would tend to use. Okay. So hopefully you remember that. Next, pressure, P. The main thing I want to identify here is that there's a difference between the actual pressure, which we'll call the absolute pressure, and the pressure that we read on a gauge. If you have a pressure gauge out there in industry somewhere, typically what you do is you just stick that gauge onto your device and you set the thing to 0. That would be called the gauge pressure. But the gauge pressure is really the pressure above atmospheric pressure. We can't escape from the atmospheric pressure. We've got miles of atmosphere above us. So when we're solving a problem, we have to be very careful that we're using the absolute pressure, that is the actual pressure. So with regards to pressure, the absolute pressure, which we can also just think of as the actual pressure, is really just the sum of the pressure that's read on the pressure gauge, the one that's basically set to 0 at atmospheric conditions, and then plus whatever the pressure is in the atmosphere. So the atmospheric pressure, at least in this class, is something that would generally be given to you. Out there in the real world, you'll have a barometer on the wall, and you'll just read the atmospheric pressure off the barometer. You'll add to it the pressure that it says on the pressure gauge on the side of your tank, your pipe, whatever, and that's going to be the absolute pressure that you're going to use in problem solving. Okay? So again, this is something you should be aware of. By the way, if they just give you a certain pressure in a problem statement, that's the absolute pressure. Okay? You're never going to have to make that conversion. But if the problem specifically says that it's a pressure gauge, and then later in the problem they tell you what the atmospheric pressure is, well then clearly you're going to have to add the two together to get the absolute pressure for use in your problem. Okay. Another property of interest is enthalpy. Okay. So enthalpy is just H, and the enthalpy is really just defined as the internal energy plus the pressure times volume. Whenever you see three lines and an equal sign, again, I assume you know this already, but if not, that just means equals. I'm sorry, that just means is defined by. So the way we define enthalpy is simply U plus PV. Now, you're never going to actually have to add U plus PV together because, frankly, you're always going to have enthalpy data. And it looks like there's a lot of glare coming in here. So, whoops. Does that help you guys out? Good. So if we have a problem that involves enthalpy, I mean, there may be times when we'll have to add U plus PV, but for the most part, we don't. The data will be available in our property tables, and we'll just use it as appropriate. Let's also note that we can divide this whole thing by mass. The total enthalpy of the mass is the specific enthalpy. The internal energy of the mass is the specific internal energy. And the volume of the mass is the specific volume. So these are both ways that we can write our definition of enthalpy. Okay. And then lastly, let me just note that we are going to use both SI as well as British units in this particular class. So make sure you're comfortable with both sets of units. Make sure you read the problem carefully so that you're using the British tables or the SI tables when appropriate. Please note also that in the SI system, for the most part, the conversion factors are just identities. In other words, just a bunch of ones. Maybe you'll have to convert, say, joules to kilojoules, so you'll have a 10 to the third here and there. In the British units, it's totally different, right? The British units are not very forgiving, so you're going to have to use all these various conversion factors that are in the inside back cover of your book. So please make sure that you know that these exist in the inside back cover of your book. You'll definitely have to use them a lot. Okay. So, again, if there's any questions, please let me know. Okay. All righty, now let's talk about property data. So first of all, there are many ways that we can find our property data, but for the most part, we're going to use tables. Now, there's only so much space in your textbook, and the author has chosen to pretty much just give you tables for water not meaning liquid water, but H2O. And then there's also data for one particular refrigerant, which is this R134A. There's other data in the book as well, but those are generally what we're going to be using as we solve problems. I'm not going to give you problems that involve ammonia or propane or any other unusual substances. We'll just look at problems that use the data that's in your book. So we use property tables. We know that there's actually different types of tables. There's the saturation tables, in other words, the data associated with either saturated liquids, saturated vapors, or two-phase mixtures. In fact, you might just want to note, for instance, that if we wanted to, let's say plot temperature versus specific volume, you know, we have our characteristic dome, that's our saturation line, if you will. You know, we know that the saturated vapor data is really just the data along the right-hand side of the curve. And we know that the saturated liquid data is just the data along the left-hand side of the curve. And if we have a two-phase mixture, that is if we're somewhere in between, then we have to use what we call the quality. So let me just give you a very brief summary of this. So first of all, the saturation data is going to exist for water or R134A. It's table A4 and A5 that has the saturation data for water, and tables A11 and A12 that has the saturation data for the refrigerant. And there's two tables simply for our convenience. It has the same data in them, right? Table A4 just lists all the data in nice uniform increments of temperature, and A5 gives you all the data but in nice uniform increments of pressure. It's the same information though, right? Same with A11 and A12. A11 is the data in temperature order, and A12 is the data in pressure order. So if we have a problem that involves a saturated mixture, or I would typically call it a two-phase mixture, or if you have a problem where you're exactly on the saturation curve somewhere, then you definitely want to get all of your data out of those two sets of tables. Now, we might also have superheated vapor, right? Over to the right of the saturated line, the saturation curve is our superheat. So this is superheated vapor. So if you're over there where you're always in the vapor phase, then you're going to use table A6 or table A13 for water and refrigerant respectively. Please note that tables A6 and 13 are actually a series of subtables, right? There's an individual table for a given pressure, and then at that given pressure, then it gives you a list of temperatures, and within the body of the table, it'll have your specific volume, internal energy, enthalpy, and entropy data in it. So again, you should all be very familiar with using the superheat tables. And then lastly, if we have a compressed liquid, that will be over here to the left. So I didn't leave myself much room here, but a compressed liquid is to the left of the saturation curve. Sometimes a compressed liquid is called a subcooled liquid, but it's the same thing. Now, the problem with compressed liquids is, first of all, that there's no data at all for the refrigerant. There just isn't a table. And then for water, the data is in table A7, but the first entry, the lowest pressure in that table, is something like 50 times atmospheric pressure, which is a pressure so high that you're never even going to have a real problem that operates in the range of the data on table A7. So personally, I didn't even know why the author bothered to put in table A7, because it's pretty much useless to us. But nonetheless, that's okay, because if we have a compressed liquid, and this only applies to a compressed liquid, we can actually make an approximation. So if we have a property y, and by the way, y could be anything, specific volume, entropy, enthalpy, internal energy, right? It could be any of those. But for a property y, for a compressed liquid, so let's say we have y for a compressed liquid at a certain temperature and pressure, that's actually going to equal, at least approximately equal, the value of the saturated liquid at the same temperature. Okay, so this equals y for a saturated liquid at the same temperature. Okay, now I underline temperature about 1,000,000 times and put an exclamation mark, because students will very often just not pay attention and look up the saturated liquid conditions at the same pressure rather than the same temperature. It doesn't work on pressure, it only works on temperature. So please make sure that if you have a compressed liquid at a particular temperature and pressure, know what that temperature is, go into the saturation table and find the saturated liquid data at that temperature. Another way I could write that is just YF at T, right? F is the subscript that we use to represent the saturated liquid. G is the subscript that we use to represent the saturated vapor, right? So make sure you are aware of these kinds of issues. And then I guess I should just note here, for any property y, specific volume, enthalpy, internal energy, entropy, that's what I mean by property y. I just didn't want to have to write out that same equation 4 separate times. And then what if we have a two-phase mixture? Okay. Hopefully we remember that we have to use what's called quality, right? So again, for a property y, again, anything VHUS, then for that, it's going to equal the value of the saturated liquid, and we would call that YF, and then plus the quality times YFG. Okay. Now again, F means saturated liquid. The subscript FG is actually the difference between the saturated vapor and the saturated liquid portion, right? So if you look into your tables in the back of the book, specific volume data only gives you the value of the saturated liquid and the value of the saturated vapor, so you actually have to physically take the difference between the two to use it in this equation above, right? On the other hand, the internal energy, enthalpy, and entropy, you already have the FG data. It would be called internal energy of evaporation or enthalpy of evaporation, or sometimes of vaporization. It's basically the difference between the liquid and the vapor. In other words, what is the difference in internal energy or enthalpy or specific volume as we move from the saturated liquid over to the saturated vapor? And that's a vaporization process, right? We start with a liquid, we end with a vapor. So that's why I sometimes call this FG term of vaporization or of evaporation. All right, so again, this would apply to specific volume, enthalpy, internal energy, and entropy. And I just didn't want to have to write the whole thing 4 separate times. Okay, so there's our two-phase mixtures. So again, any questions on any of this? Yeah.
Could you repeat what Y sub G and Y sub F are?
Yeah, F represents the saturated liquid, so all the data on the left-hand side is the saturated liquid data. So F means sat liquid, and G represents the saturated vapor. So at any particular temperature, we can go into A4 or A11, or at any particular pressure, we can go into A5 or A12, and you'll see the first column will be saturated liquid data, the next column will be saturated vapor data, or in some cases, saturated liquid, then the evaporation, and then the vapor data. Okay. By the way, some books will use L and V instead of F and G, L for liquid, V for vapor. But you can think of F as fluid, liquid, G as gas or vapor, just to make sure that you remember. So that's where those terms come from. Okay. So let's move on. Now, it is possible, instead of using property tables, to actually use equations. And we call these equations of state because it relates different thermodynamic properties at the particular state of a particular substance. So these are called equations of state. Now, the only equation of state that we really would like to use on a regular basis involves the ideal gas. So the ideal gas equation of state is something that you were all exposed to. There's various forms. That's one form of the ideal gas equation of state. Here's another form of the ideal gas equation of state. Here's another form of the ideal gas equation of state. They're just different ways to relate ideal gases. Now, if you go into your textbook, and I can't even tell you what the page is anymore, there's a little test so you can determine whether a gas is an ideal gas or a real gas. But I'm not even going to worry about it in this class. We're generally not going to be dealing with real gases. This is just your second course in thermodynamics, and it's hard enough to understand the basic concepts. So when we deal with gases, we're exclusively going to deal with ideal gases in this class. So don't ever worry about taking that little test. I think it's on page 139, if I'm not mistaken. But don't even worry about that. Just assume that it's an ideal gas and use the methods that will be discussed in class for solving problems involving ideal gases. Nonetheless, these are just different versions of the equation of state. Let's keep in mind that R and RU are different, right? R is the gas constant for a specific, maybe I shouldn't even use the word specific, is a gas constant for a given gas. And the data is going to be in table A2. That's where you're going to find the gas constant data. And the data is going to have different units than RU. RU is what we call the universal gas constant. And the universal gas constant is also in the inside back cover of your book with like 7 different sets of units. So if you're solving a problem and you need the universal gas constant, again, just go to the inside back cover and choose the term with the right units consistent with the problem that you're trying to solve. And let us note that the only difference between the universal gas constant and the gas constant for a particular gas is its molar mass. If you just simply divide the universal gas constant by the molar mass, then that's going to give you the gas constant. Now, you're never going to have to actually do that. If you have a gas like oxygen, just go into table A2 and look up R. You don't have to. You can go into table A2, look up the molar mass, go into the appendix, look up RU, divide one into the other. I mean, why spend all that time, right? Just look up the value of R. Nonetheless, they are going to be different, R and RU. And again, M is our molar mass. When I was in college, we called that molecular weight. I wonder if in chemistry they still call it molecular weight, but nowadays everybody calls it molar mass. I have no idea why there's that change in terminology over the last 30 or so, 40 years now, gosh. And, well, but there is, so. Nonetheless, this just is a little bit about gas constants. Okay. Another thing that we should be aware of are called specific heats. And specific heats are used in problems that generally involve ideal gases. Okay? So there's actually 2 of them. There's CP and CV. CP is called specific heat at constant pressure, and CV is named specific heat at constant volume. It has absolutely nothing to do with whether it's a constant pressure or a constant volume process, right? These are simply defined as partial derivatives. The partial derivative of the specific enthalpy with respect to temperature holding the pressure constant is what we call specific heat at constant pressure. And the partial derivative of specific internal energy with respect to temperature holding the volume, well, really specific volume constant, is what we call specific heat at constant volume. So you can see why we call them at constant pressure and at constant volume. It has to do with the way we take the partial derivatives. Right? If we take the partial at a constant pressure, it's called specific heat at constant pressure. If we take the partial at constant volume, it's called specific heat at constant volume. That's really all there is to it. We're never actually going to take these partials, right? Just find the data. The data is also in table A2, and that's where you're going to find your information. So, any questions? Now, we do use this a lot. Oh, I think I lost my cameraman, and he's pointing it that way. So I guess I can make funny faces over here now, right? Nobody will know. Well, I'll try to behave. All right, so one thing we use specific heats for a lot is for problems that involve ideal gases. So let's continue here with ideal gases. So for ideal gases, we would note that the enthalpy is a very strong function of temperature, but a very weak function of pressure and specific volume. And the same with internal energy. It's a very strong function of temperature, but not really a strong function of volume or pressure. So we could actually make the approximation that dH is going to be approximately equal to Cp dt, and du is going to be approximately equal to Cv dt. This was hopefully derived and explained to you in your thermo class. Well, your first thermo class. So once we have these, then for most problems, we're trying to find a change, right? We have a process that begins at state point 1 and ends at state point 2. Or maybe it's a steady flow process where we enter a device at state point 1 and leave at state point 2. So what we're trying to do is actually find a change in internal energy or enthalpy for a problem. And these are all going to be first law problems. Hopefully you're all aware of the first law and how basically everything that we're going to cover is first law problems with various modifications. But nonetheless, we could then find an enthalpy change or an internal energy change simply by integrating over temperature, right? Again, Cp and Cv are really only strong functions of temperature and nothing else. So the integral from T1 to T2 of Cp dt is how we find our enthalpy change. And our integral from T1 to T2 of Cv dt is how we find our internal energy change. Okay. Now, are we ever going to actually have to take this integral? No. I mean, we could. We can go into table, I guess it's A2 part C, where it gives you a polynomial equation that relates Cp, or it'll show you how, but it'll also relate Cv to temperature. And you can plug it in, and you can do the integral. I mean, it's simple. It's a polynomial. But we don't need to do that. We have easier ways to take care of that. And that's something that we'll be talking about eventually, but not quite yet. Nonetheless, let's move on. Okay. Another thing that we're going to need for ideal gases that involves these specific heats is the ability to find the entropy change for a process. You've all learned about entropy. Hopefully we understand that entropy gives us the ability to determine how close to ideal a process is, or even whether that process is possible or not. That's what entropy is all about. So we would have found in your thermo class that the entropy change can be found this way. Just the integral of Cv dt over T evaluated between T1 and T2, then plus R times the natural log of V2 over V1. And those are specific volumes. V2 over V1. Or we can find the entropy change by integrating between T1 and T2 of Cp dt over T, and then minus R times the natural log of P2 over P1. Okay. So this is how we'll be able to find our entropy change. Now, I mentioned that there's simple ways to find these, that we don't really always have to do the entire integration. So one of the easiest ways is just assume that Cp and Cv are constants. Okay. So again, we're still talking about ideal gases here. For constant Cp or Cv, and this could be either at room temperature or at the average temperature of the problem. Okay. But nonetheless, if we assume that Cp or Cv are constant, and again, either at the room temperature or at some average temperature, then it makes the integration essentially trivial, right? If Cp and Cv are constants, that comes out of the integral, and the integral of dt is just T. Or for the entropy, if we're able to pull Cp out or Cv out, then the integral of dt over T is just the natural log, right? So it's very easy to do these integrations, and we would just end up, again, if these are constant values, then we would find that H2 minus H1 is just Cp times T evaluated between 1 and 2. In other words, T2 minus T1. The internal energy change is Cv times T2 minus T1. The entropy change is going to be Cv times the natural log of T2 over T1 plus R natural log V2 over V1, or Cp times the natural log T2 over T1 minus R natural log P2 over P1. Okay. So certainly, if we're solving a problem that involves an ideal gas, the easiest thing for us to do is to just assume that Cp or Cv are constant, and then we end up with these nice, simple equations. Okay? Now, we're not always or only going to be looking at the situations where Cp and Cv are constant. Okay? There will be other situations where we will assume that Cp and Cv are variable. And we'll start talking about that here in just a moment. Well, actually, I'd only have a few moments left, so actually it's about the first thing we'll cover on Wednesday. By the way, even though I'm calling this review, even on Wednesday is review, when we start talking about variable specific heat, it is something that in my thermo class, my 301 class, we specifically did not talk about variable specific heats. In other words, specific heats that are functions of temperature. So we are going to talk about that on Wednesday. So it's not entirely a review day, maybe for many of you, but certainly not all of you. All right, so this is how we're going to find our data. One last note regarding ideal gases here is that R, the gas constant, is actually the difference between the specific heat at constant pressure and the specific heat at constant volume. Again, we're generally not going to have to actually apply this equation, but we should at least know that this is true. And then let's also note that for many problems involving ideal gases, we're going to need to know the ratio of Cp over Cv, and we call that ratio K. So again, K is not something you'll actually have to calculate. It's just something that you're going to find in table A2. I think it's the very last column of data, and you'll just have to pull it out. So we're not done with the review, but this is all the time I have for today. The next thing we're going to do is talk about, well, what if you have an isentropic process? In other words, if these equal 0, what kind of equations can be developed from that? And again, we'll start talking about this on Wednesday. So that's all for today. I'll see you guys on Wednesday. Please note the review homework problems all due next Wednesday, so please make a note of those. And I will see you all then.